Hi guys, we have last class started the sense organs and in this category we have completed that is what is called the photoreceptor, the human eye. Now let's proceed further about other sense organ, the important organ, the organ of hearing and body balance. Now we have the human ear. So ears are phonoreceptors because they are concerned with the perception of sound waves. But they perform two important functions in addition to hearing. They are also involved in maintaining the body balance and posture of the body. So they perform two important functions. One, that is a hearing process, another one, maintenance of body balance. Now let's see some of the anatomical structures related to our ear. The ear consists of three important parts: the outer or external ear, then the middle ear, and also the last one, the internal ear. Let's see one by one the various components, because you have studied already about the anatomical characteristics of human ear in your earlier classes. A little bit value to be added for this one. Now the outer ear. It consists of the external ear pinna, then a canal, what is called auditory canal, the external auditory meatus, and the third one, the tympanic membrane. So it is being formed of three important structures: the pinna or ear lobe, and it is being supported with that one elastic cartilage. The second one, the external auditory meatus or external auditory canal, and finally we have the tympanum or the tympanic membrane. Now the pinna, what I mentioned already, it consists of just we have elastic cartilage and also the vestigial muscles like auricular muscles. For the movement of the ear lobe, what we had in the past in our ancestors, we had auricular muscles. Now it has been reduced so that we cannot move the ear lobes, and that is an example for vestigial organ. Now it is supported with cartilage. What type of cartilage? Elastic cartilage. Now the main function of the ear lobe is simply perceiving the sound vibrations in the air. Now the second part, what we get, the external auditory meatus, it is nothing but a tube or a canal which is leading inwards and extends up to the tympanic membrane, which is the block between the external ear and then what is called the middle ear region. Now in the external auditory meatus as well as in the earlobe, we have very fine hairs are present along with wax secreting glands, which are nothing but modified sebaceous glands. Such wax secreting glands which are present in the external auditory meatus are called ceruminous glands. The wax secreting glands are called ceruminous glands. They are modified sebaceous glands. So also we have fine hairy structures present in the external auditory meatus and also in the pinna. So now the wax secretion is responsible for trapping the dust particles so that we can collect the dust particles, and that should be removed one after another just frequently. Otherwise normally the wax secretions along with the hair, along with the dust particles harden into stone-like structures which will strike against the eardrum and affecting what is called the hearing process. So the ceruminous glands are the wax glands secreting the wax, and they are nothing but modified sebaceous glands. Now the next part, what we have, the tympanic membrane, the partition between the external ear and the middle ear region. Now the tympanic membrane is actually formed of connective tissue. On the outer side towards the external region, it is lined with the skin or covered with the skin. On the inner side, it is covered with what is called a mucous membrane. So this is the arrangement. The tympanic membrane can be vibrated by means of sound waves, and that vibration can be transmitted to the internal ear region through the ear ossicles of the middle ear. Then only we can hear the sound waves. If there is any perforation in the eardrum, it leads to what is called the deafness, may be caused because of sudden explosion or head injury. So sudden explosion or head injury may cause the rupture of the eardrum, leading to the deafness. The person is unable to hear. Now the middle ear region. The middle ear is nothing but a bony cavity, the temporal region. It's nothing but a air-filled bony cavity, not a vacuum, air-filled bony cavity just in the temporal bone. This bony cavity consists of a chain of three bones together called as ear ossicles or auditory ossicles. They are from external to the internal side: malleus, incus and stapes. Now these are all actually arranged just in such a manner they can transmit the vibrations produced by the tympanic membrane to the oval window of the cochlea. Normally, the malleus, which is more or less hammer-shaped bone, is attached to what is called the tympanic membrane. The last bone, the smallest bone in the body, namely the stapes bone, which is attached to, that is the oval window of the cochlea, and in between which we have just, for example, incus, which is articulating between these two. So these three are acting as what is called a lever, responsible for increasing the efficiency of transmission of sound waves. That is, they can amplify the sound waves. They are acting as a lever responsible for increasing the efficiency of sound waves. That is, they are responsible for amplifying the sound vibrations. That is normally what we have. So the malleus is attached to the tympanic membrane, the stapes is attached to the oval window. I mentioned already these ossicles together act as levers and increase the efficiency of transmission of sound waves, nothing but amplifying the sound vibrations. Now there is a canal, a tube joining, that is a middle ear with what is called the nasopharynx, a part of the pharynx, and that is called Eustachian tube. Now this tube equalizes the pressure or keeps the pressure equal on either side of the eardrum. Hearing will be normal only when the pressure in the middle ear and the external ear, or we have the atmospheric air, should be equal. And that should be done because of the Eustachian tube. So we are swallowing the air while just, for example, while talking, while just actually even sneezing or while swallowing, some amount of air has been transported through this Eustachian tube to what is called the middle ear region. Suppose when you are infected with a common cold, what will happen? There is a blockage of this Eustachian tube by phlegm. The mucus normally blocks the passage, so the pressure will not be equal on either side of the eardrum. In the middle ear region, somehow the pressure has been decreased. It is not equal to the atmospheric pressure. So hearing will not be normal when this Eustachian tube is blocked with the phlegm at times of cold. Now here is a structure. So this part, what we have, the green part, the external ear up to this region, external ear region. The pinna, the external auditory meatus. Now this is the eardrum made up of connective tissue. On the outside, it is being normally lined with the skin. On its inside, it is lined with what is called a mucous membrane. Then we have the middle ear region. We have a chain of 3 bones called auditory ossicles. Now this is the hammer-shaped bone, what is called the malleus. Then we have incus, and this is what is called, this is anvil shape and this is stirrup shape. It is found attached to the oval window of the cochlea. And now this is the Eustachian tube arising from the middle ear region, connected to the nasopharynx of the pharynx, and normally responsible for keeping the pressure equal on either side of the eardrum, this side and this side. So hearing will be normal only when the pressure is equal on either side of the eardrum. And now we have the internal region. This internal region is normally formed of actually a labyrinth. The internal area is otherwise called as labyrinth. It's being once again divided into 2 parts. One is called the bony labyrinth, another one membranous labyrinth. The bony labyrinth is nothing but just actually a series of channels. And now this membranous labyrinth is normally found inside this bony labyrinth, surrounded by perilymph. Whereas the membranous labyrinth contains what is called endolymph. I will give you a clear picture about this one in the next one. Now, this is the internal region. The internal ear normally formed of the different components. We'll see once again later the same figure in a different form for just showing the different components in a different manner, but the same components what we have. We'll see once again later about this one. Now the inner ear. Now actually the inner ear is normally filled with the fluid. So this fluid filled inner ear is called as a labyrinth. It is called as a labyrinth. The internal ear is otherwise called as a labyrinth. This labyrinth consists of 2 important parts what I mentioned earlier. One is called as the bony labyrinth. Another one the membranous labyrinth. I mentioned earlier the bony labyrinth is nothing but a series of channels. And whereas actually inside these channels, the bony labyrinth channels, or we have the canals, lies the membranous labyrinth, which is being surrounded by what is called perilymph. So the bony labyrinth, otherwise we can see filled with what is called the perilymph. In that one only we have what is called the membranous labyrinth. So the bony labyrinth is in the form of series of channels where you have inside the membranous labyrinth is being formed, which is being surrounded by what is called a fluid perilimb. And whereas the membranous labyrinth is filled with endolimb. So the bony labyrinth is filled with perilimb and the membranous labyrinth is filled with endolimb. And the membranous labyrinth lies inside what is called the bony labyrinth. You will see in the picture in the diagram later. I will show you. Now, what are the components of the internal ear? If you are taking the membranous labyrinth, it consists of the following components. 1. Just we have the cochlea, the main organ of hearing. Number 2, the vestibular apparatus, the main organ of maintenance and balance. So, cochlea, the organ of hearing, and vestibular apparatus normally just actually the organ of body balance. Now, cochlea. This cochlea is a coiled portion, 2.5 turns. 2.5 turns. It's actually 2 full turns and 1 half turn, just like a snail shell. Now, the membranes of the cochlea, namely resinous membrane and basilar's membrane, divide the surrounding perilimb into, that is, 2 canals. The membranes of the cochlea, normally divides. There are 2 membranes, we can see. The membranes of the cochlea divide, that is what is called the bony labyrinth, into 2 parts. The upper part is called scala vestibuli and the lower part is called scala tympani, both being filled with what is called the perilimb. So we have the membranes of the cochlea divided. There are 2 membranes. One is called the upper membrane, what is called the resinous membrane. Another one, what is called the basilar membrane. These 2 membranes together divide the entire bony labyrinth into upper canal and lower canal. The upper canal is called scala vestibuli and the lower canal is called scala tympani, and both are filled with a fluid what is called perilimb. Now we see that one. Now this is the cross section of the cochlea and this is the upper canal and this is the lower canal. This is what is called scala vestibuli, this is called scala tympani, and both being divided by means of 2 membranes. Now this is what is called the resinous membrane and this membrane is called as what is called the basilar membrane. So we have 2 compartments of what is called the bony labyrinth, and this is what is called actually the cavity of the membranous labyrinth. So the cavity of the membranous labyrinth is called scala media, which is filled with endolimb. So anyway, normally the cochlea, the membranous labyrinth is being formed inside the bony labyrinth. The bony labyrinth being divided into 2 compartments by means of 2 membranes, upper membrane, resinous membrane, lower membrane, basilar membrane, and these 2 cavities are filled with perilimb. So this is scala tympani and this is scala what is called vestibuli, or otherwise called vestibular canal and tympanic canal. Then we have just added the membranous labyrinth encloses a canal which is called scala media, which is filled with what is called endolimb. We'll go back once again the components. So I mentioned already the space within the cochlea, namely the membranous labyrinth, is called scala media and that is filled with endolimb. So the bony labyrinth is divided into 2 compartments by the 2 membranes of the cochlea, namely upper scala vestibuli and lower scala tympani, by means of 2 membranes, namely resinous membrane and also the basilar membrane. And now the space within the cochlea, just actually what we can say otherwise the membranous labyrinth, is normally called scala media because it is a median canal filled with a fluid endolimb. Now at the base of the cochlea, so we have the 2 canals. What we have just scala vestibuli and scala tympani. At the base of the cochlea, the scala vestibuli ends at what is called an oval window, otherwise called fenestra ovalis. Fenestra ovalis. And while the scala tympani ends at what is called the round window, or otherwise called fenestra rotunda. Fenestra rotunda. This is fenestra ovalis and this is fenestra rotunda. And this round window opens into the medullary region. Now this oval window is actually conducting the vibrations from what is called the chain of bones into the perilimb of the scala vestibuli. Whereas the round window normally conducts the extra sound waves into the medullary region, which is being sent out through the eustachian tube. That is a mechanism. Now the scala vestibuli and the scala tympani are connected through what is called helicotrema. a small opening present at the distal end of the cochlea and apex of the cochlea. Helicotrema is a small opening allowing actually the passage or allowing the connection or allowing the communication of the scala vestibuli with the scala tympani. And now this is actually a narrow opening. And so that we can have scala vestibuli and scala tympani continue at the distal end through this opening, namely helicotrema. Now this is the cross section once again we have. So you see, this is what we call the cochlear region. I'll show another one. So now this is the arrangement. It's better when compared to the previous ones. The whole structure represents the internal ear. Now this is the cochlea. And now this one is what is called the vestibular apparatus. All these things together called as vestibular apparatus. Now the cochlea is a coil structure. Now the outer one what we have, this is what is called the bony labyrinth, and now this is what is called the membranous labyrinth. You could see here. So the membranous labyrinth lies within the bony labyrinth, now which is being surrounded by perileaf. Now this one actually, as a result of the two membranes of the cochlea, this is membrane 1 and membrane 2, we have two membranes, not clear here. The two membranes separate the perilimb of what is called the bony limb into two compartments, and this one is outer or upper scala vestibuli and this one is the lower scala tympani. This is what we have just with the reference I represented here, but here you have to see that one. Not there you have the scala vestibuli and scala tympani, and here only we have just what we have the scala vestibuli and scala tympani. So now here suppose this is the scala vestibuli and here the scala tympani, and now this is the cavity or the space of this what is called the cochlea, otherwise called scala media, filled with a fluid. The name of the fluid what is called endolimb. The name of the fluid what is called endolimb. Now just we have seen about the cochlear compartments. So I see actually the scala vestibuli and the scala tympani which are communicating through the helicotrema. I will go through what are the other structures or the components. Now when you make a cross section of the cochlea, it shows three compartments. Now the SV refers to the scala vestibuli, now ST refers to the scala tympani, and SM refers to the scala media. And these two are the canals of what is called the bony labyrinth, and this one is the canal enclosed by the cochlea, the membranous labyrinth filled with endolimb. And now this is the arrangement. Now the organ of Corti. We are talking about the cochlea, not the vestibular apparatus. Now there is a sensory structure. The organ of hearing is situated on the basilar membrane of what is called on the basilar membrane of the cochlea. So that structure located in the basilar membrane of the cochlea is called as organ of Corti. It is being formed of three types of cells. Hair cells. Number one, hair cells. These are the original auditory receptors concerned with the hearing. It also contains what is called the basal cells, otherwise called the data cells, and the supporting tissues or supporting cells, what is called cells of Hensen. So there are three types of cells which together form the organ of Corti. One, the hair cells, otherwise called as auditory receptors. Another one, the basal cells or the data cells. The third one, the supporting cells, also called as the cells of Hensen after the name. Normally the hair cells are arranged in the form of rows on the inner side of the organ of Corti. And now this organ of Corti was actually represented by an Italian scientist, that is Alfonso Corti, that is what the name is given as organ of Corti. So the auditory receptors, maybe the organ of Corti, was first reported by an Italian doctor by name Alfonso Corti, that is what the name is given as organ of Corti. So the hair cells, namely the auditory receptors, are present in a row, normally found in rows, on the internal side of the organ of Corti. Now, at the basal end of each hair cell is present an afferent nerve as well as efferent nerve, because normally each cell is associated with an afferent nerve for just carrying impulses towards the brain, and also we have efferent nerve fiber. So the basal end of the hair cell is associated with an afferent nerve fiber for carrying the action potential towards the auditory cortex. Now, this is the organ of Corti. I mentioned already the organ of Corti is situated on the basilar membrane. Now, this line represents the basilar membrane. Now this is the organ of Carti. Now this cavity is called scala media. This is a scala media region, scala media. Now the organ of Carti mainly consists of hair cells or auditory cells, sensory hair cells. And now we have OHC. These are all outer hair cells. And now IHC referring to the inner hair cells. Now the outer hair cells normally having just actually some processes projecting from its distal end or just a free end, and they represent what are called the stereocilia. Some processes projecting from the distal end of the hair cells at the tip are called stereocilia. Now this is what we have the data cells, the basal cells, above which only we have the hair cells. So this is internal hair cell and that one is external hair cell. Now these hair cells actually, there is internal and just actually inner and outer. So the outer hair cells also have lateral membrane along with stereocilia. So outer hair cells, inner hair cells, the outer hair cells have membrane along with the cilia, and now this is actually that is the inner hair cells, IHC referring to the inner hair cells. And now there is a nerve fiber originating from these hair cells. You see that one, these are all the afferent nerve fibers leading to the auditory cortex through auditory nerve. So these are the afferent nerve fibers associated with the base of these hair cells, and they form together the auditory nerve carrying the impulses towards the auditory cortex. Now another diagram referring to the same one, you see that one, this is the inner hair cells and that is outer hair cell. Inner hair cell, outer hair cell. Now we have also the hair cells are supported by data cells and also what we have outer pillar cells, inner pillar cells, outer phalangeal cells, inner phalangeal cells. I will show you the next picture. See that one. So this is an enlarged one. You see that one, normally the hair cells are found embedded above a thin gelatinous elastic membrane, and this thin elastic gelatinous membrane where you have the hair cells are embedded is called as a tectorial membrane, which is originating from the base of what is called the median canal, from the base of the median canal or from the base of the cochlea. Now we have just see that one, the hair cells, we have inner hair cell and then outer hair cell. This one outer, just the outer hair cell, here the outer hair cell. So these are provided with actually just a tuft of just processes projecting from that one, and they form stereocilia, or we have also kinocilia. Stereocilia, kinocilia. You could see that one here, the organ of Carti is found embedded in a thin elastic gelatinous membrane, what is called as a tectorial membrane. Now the hair cells are actually provided at the base. You have the afferent dendrites or the afferent terminals, and also provided with efferent terminals. Afferent terminals and efferent terminals, nothing with the nerve fibers. And we have, you see, associated with these hair cells, we have the pillar cells, maybe outer and inner pillar cells, and also we have some head plates are present near the top, and also we have phalangeal cells. Phalangeal cells. Like you see that one, outer phalangeal cells and inner phalangeal cells, there are also some processes when you are going deep in structure. This is the outer structure, not detailed, you have to know simply. So we have the outer hair cells, inner hair cells, they are provided with the cilia, they are called the same stereocilia, and these cells are found embedded with a thin gelatinous membrane above, and that is called tectorial membrane. So I mentioned already from the top or from the distal part or from the apical part, a large number of processes called stereocilia are projected from the apical part, what I mentioned, the same one. So the sensory hair cells are found embedded above in a thin elastic gelatinous membrane called the tectorial membrane. So that's about the organ of Carti, the real organ of hearing situated on the basilar membrane of the cochlea. Now the second part, vestibular apparatus, it is concerned with the balance. So the organ of Carti is a real organ of hearing, whereas the vestibular apparatus is concerned with what is called the body balance and posture of the body. And this is nothing but a complex structure lying above the cochlea. It consists of, number one, 3 semicircular canals and two just actually sacs called reticule and saccule with some structures for just creating action potential, what are called the ear stones or otolith organ. So the vestibular apparatus is a complex system found above the cochlea concerned with the body balance, and now it is being formed of three semicircular canals and two sac-like structures. One is reticule, another one is saccule, and both contain otolith organs. And they are responsible for just generating action potential because of the wave what we have. Now semicircular canals. Normally there are three semicircular canals, two vertical and one horizontal in each. And each end of what is called the semicircular canal ends in a swollen structure, and that structure is called ampulla. That structure is called ampulla. You see that one here. So there are two vertical canals. These two are the vertical canals actually, and one horizontal. This is horizontal canal. And each end of what is called the semicircular canal ends in a swollen structure, what is called ampulla. Ampulla. So the ampulla is nothing but the swollen part of the semicircular canal only at each end. Now the above one we have the vestibular apparatus, and the vestibular apparatus, the complex system, consists of the three semicircular canals and then the two sac-like structures, what we have the reticule and saccule. Normally you know that from the oval window, this is actually the oval window in communication with the, that is the cochlea, and this is what is called the round window, which is in communication with the middle ear region. So which is actually normally extending the sound waves, or extra sound waves can be transmitted all along through the what is called the scala tympani, and then through this scale, that is a round window, to reach the middle ear region, from where it is being centered through the nasopharynx via the eustachian tube. Now, so two vertical and one horizontal. Now the inner structure is not given. What are the inner components of this one ampulla? Now this ampulla is provided with a sensory ridge, a projecting sensory ridge, and that is concerned with what is called the body balance. Now the ampulla contains projecting sensory ridge. The name of the sensory ridge is called crista. As it is found in ampulla region, it is called crista ampullaris. The sensory ridge projecting from the ampulla is called crista ampullaris, and which only contains the sensory hair cells. At the tip of hair cells we have a calcium carbonate crystal or a stone like this. Now this is a sensory hair cell, this is the hair cell, and now this is the hair, and this one is the otolith. This is what is called otolith. This is otolith, the calcium carbonate crystal lying at the tip of actually what is called the flagella or the hair. So the base of the canal, now the ampulla contains a projecting sensory ridge. The name of the sensory ridge is called crista ampulla, crista ampullaris, which has hair cells, and these hair cells are found embedded in a gelatinous, dome-shaped gelatinous structure, and that is called cupola, which is lying above this one. So the crista is found embedded in a gelatinous, a dome-shaped gelatinous structure called cupola. So crista and cupola. Cupola is nothing but a gelatinous dome-shaped structure in which is found embedded the sensory ridge, namely the crista of ampulla. Now the saccule, and again just like what is called the ampulla, the saccule and reticule. So they are nothing but actually the vestibular apparatus, one component. Another component of vestibular apparatus, the saccule and reticule contain again a projecting sensory ridge. Here it is called macula. It is called macula. So it is also found embedded in gelatinous material, and it is also having hair cells. The hair cells normally contain what is called calcium carbonate crystal, a calcium carbonate stone or a calcium carbonate granule. Just actually at the tip of the hair cell, what I mentioned, they are called as otoliths or the ear stones. So the macula as well as crista of semicircular canals ampulla contain hair cells. The hairs at the tips contain what is called granules of calcium carbonate. They are floating in a medium of fluid, what is called, that is the endolymph. And these crystal or the stones of calcium carbonate are oscillating when there is a change in posture. When there is a change in posture of the body, so a wave is created in the limb, and as a result the stones are also oscillating present at the tip of the stones. They set up now impulse in the form of action potential that is being relayed to the brain so that the person can adjust his body posture and balance. So the crista and macula and both have sensory ridges, and they have hair cells. At the tip of the hair cells we have granules of calcium carbonate, and these granules of calcium carbonate are called the ear stones or otoliths, and they are all oscillating when there is a change in posture of the body because they are floating in a lymph, what is called the perilymph. Floating in a limb, what is called the endolimb. And so that what will happen, a nerve impulse being set up, and that is being carried away by the auditory nerve, that is a cochlear nerve, or we can say for example auditory nerve, which contains acoustic as well as this what is called the body balance maintenance nerve, which carry the impulses towards the brain so that the brain sends order to the body to change the posture and to maintain the balance. So anyway, the cristae and maculae are specific sensory structures, or they are considered as receptors of the vestibular apparatus that concern with mainly the body balance and the posture of the body. This is because of the oscillation of the hair cells with otoliths that set up nerve impulse, and that is responsible for creation of action potential, and that is being transmitted away by the audit nerve to the brain so that the person can just adjust his body posture and also maintain his body balance. Now what is the mechanism of hearing? So the body balance is because of the otoliths, the calcium carbonate crystals present at the tip of the hair cells of the cristae and maculae. Now mechanism of hearing. So the external sound waves are, you know, that when heard by or received by the external ear lobe, and that is being transmitted to the auditory, just transmitted to the tympanum through the auditory meatus. So external ear receives sound waves and directs them to the eardrum. So what will happen once the sound waves reach the eardrum, striking the eardrum and making it to vibrate? Now this vibration, just the vibration of the eardrum makes movements the ear ossicles. They act as levers and transmitting the vibrations towards what is called the oval window. So the vibrations are making the movements of the ear ossicles, which transmit it in the form of movements of actually the bones towards just normally, because it is acting as a lever system and amplify the sound vibrations. That is acting as a lever system because of actually the arrangement of these ear ossicles. And there is a movement in the ear ossicles, and now what will happen, that movement of the ear ossicles makes some vibrations in the oval window of what is called the cochlea. Now the oval window is vibrating. Now the oval window is normally in adjacent with, suppose this is the oval window, we have, just suppose we are taking the ear region. This is the basilar membrane, and this is scala vestibuli, scala media, this is a scala tympani, and this is a scala media. Scala vestibuli, scala media, and scala tympani. Now this part is called the helicotrema, the opening allowing the communication between scala vestibuli and scala tympani. Now this is the basilar membrane and this is the racemous membrane. Now on the basilar membrane only we have the organ of Carti. Now this is the organ of Carti with the hair cells. So what will happen, normally this is oval window and here we have the round window. Now this is the medullary region. Now once the sound waves are reaching the oval window, making it vibrate. So the vibrations of the oval window creates waves, what is called in the perilymph of the scala vestibuli. They are also reaching the scala media and vibrating what is called the basilar membrane, and so also the hair cells. So that the bending of hair cells occur because of actually the vibration. So the ripple wave of vibration can be produced on the basilar membrane. This is because of the wave in the perilymph and then in the endolimb. Now the wave in the endolimb creates some kind of what is called wave on the basilar membrane, making the hair cells to bend. Once the hair cells are bending, what will happen? And now impulse or action potential being generated in the corresponding hair cell, and which is being transmitted by the afferent nerve. and which is being conveyed to the auditory cortex of the cerebrum via the auditive nerve. This is the mechanism what we have. So sound waves perceived or received by what is called the earlobe, transmitted to the eardrum to the external auditory meters and making what is called the eardrum to vibrate, and these vibrations are transmitted, which these vibrations make movements in the ear ossicles which act as lever and amplify the sound vibrations and transmit to the oval window, making the oval window to vibrate. When the oval window is vibrating, waves are created in the perilimb and that also in the endolimb of the scalar media. And now this endolimb wave just actually disturb the basilar membrane. So a wave or ripple is created here also, and as a result of the disturbance of the basilar membrane, the hair cells also disturb and they are bending. That bending of the movement of the hair cells set up action potential, which is normally produced in the afferent nerve fiber present at the base of the hair cell and conveyed to the brain through the auditory nerve to the auditive nerve to the what is called the auditory cortex of the temporal lobe, where interpretation occurs so that you can hear the sound waves. This is a mechanism what we have, a simple mechanism. So I mentioned here, so what will happen? Generation of action potentials in the associated afferent neurons which will send impulses to the brain via the auditory nerve. Now here is a mechanism of hearing. What is happening? So collection of sound waves by the ear lobe. Transmission of sound waves by what is called the external auditory meters. Now the vibration of what is called the tympanum. Now the movement of ear ossicles, you see that from the arrow marks, and then the vibration of this oval window. Now waves in the perilimb. Now we have waves in the perilimb. The extra sound waves being actually transmitted through the scalar tympanic and then sent out through what is called the round window and then via the esophageal tube and then via the pharynx to the outside through the mouth. And now what is happening? You see that one, the sound waves, the waves in the perilimb also makes waves in the endolimb which disturbs the basilar membrane. So that what will happen? The action potential is generated in the related afferent nerve and that one being conveyed to the brain via the auditive nerve that results in hearing process. So it is a complicated process. This is because of actually the physical vibrations are converted to electrical impulses. First with the physical vibrations, you see that one, the sound waves, we have the physical vibrations and transmitted by the ear ossicles, and the sound vibrations are converted into what is called waves in the fluid, and such waves only just normally disturb the membrane and that results in the generation of the electrical impulse, otherwise called what is known as action potential, which is being transmitted to the brain, particularly the cerebral cortex, particularly the auditory area, that results in hearing process. Now here is what we have I represented. So another one. So we have the maximum site of distortion of the organ of cortex, that is disturbance. It is being disturbed. The maximums actually we have, the distortion means somewhat actually it has been changed from its original position. So the site, the place of maximum distortion in the organ of corti is normally determined by the frequency of sound. The site of maximum distortion, where you have maximum disturbance or alteration in the organ of corti, that is being determined by the frequency of sound. That is being determined by the frequency of sound. For high pitched sounds, the maximum height of waves, you see that one near the base of the cochlea. For high pitched sound, and now this is the height of waves, we have just near the base of the cochlea. For low pitched sound, we have the maximum height of waves near the apex of the cochlea. So this is the maximum height of waves for high pitched sound near the base of the cochlea, and this is what is called the maximum height of waves, the red one, just nothing but actually at the apex of the cochlea. So this is what we have. This is for high frequency sound and this is for low frequency sound. So the site of maximum distortion in the organ of corti is simply determined by the frequency of sound. So the maximum height of waves you can have at the base for high pitched frequencies or for high frequency sound, and you have the low frequency sound, the maximum height of waves near the apex of the cochlea. So accordingly only now the waves are created, and accordingly only we can hear the sound waves for various frequencies. So the disturbance to the organ of corti you have the maximum rate of distortion, that is a disturbance in the organ of cortex, mainly determined by the frequency of sound waves. So we have the maximum height of waves near the base of the cochlea for high frequency sound and or high pitched sound or high frequency sound, and the maximum height of waves for low frequencies or just low pitched sound just at the apex of the cortex. So accordingly, we can have now these impulses are being just actually conducted towards the cerebral cortex, the auditory cortex, where they are being interpreted, resulting in hearing process. So that is the mechanism what we have. So according to the different kinds of frequencies, we can hear the sound wave. This is because of the functioning of the cochlea, the organ of cortex. So with this I concluded just about the various sense organs, particularly eye and ear in our syllabus what we have. The next lesson we have to pass on to the chemical coordination. As I would like to conclude this one, I would like to start that the next chapter, that is chemical coordination, the next class. Till then.